Let's continue our discussion here in fluid mechanics under the topic buoyancy. Now in this video, we will solve the three remaining problems in the handout. That's the problem number 4, 5, and 6. For number 4, there's a block of wood floats in water with 60 mm projecting above water surface. When placed in another liquid, so this same block of wood, when placed in another liquid with specific gravity of 1.2, the block projects 80 mm above the liquid surface. Find the height of the block of wood. So for the figure, so it's the same block of wood but in different liquid. So here is our first scenario. Our first scenario is that the block of wood is in water, and the second scenario is in a liquid of a specific gravity 1.2. Now what we're looking for here is the height h. The height h of this block of wood. So same height. So using our principles in buoyancy, we have here same weight because we have the same material. So this is W. So same weight here. But there will be a different buoyant force. So this is buoyant force 1, and then this is buoyant force 2. The reason is because they are in different liquid, or the wood is in different liquids, and the immersion here in the first scenario, the projected height is 60 mm. So this is 0.06 meter, and for the liquid specific gravity 1.2, the block projects 80 mm above the liquid surface, so 0.08 meter. So this is h minus 0.06, and this is h minus 0.08. Now since we have the same W, so if we have summation of forces vertical here, so here is W is equal to buoyant force 1. Here we have W equals buoyant force 2. Therefore, buoyant force 1 is equal to buoyant force 2. Okay. So if that happens, therefore, we need the gamma of the liquid. So here, in terms of water, and or that is, let's just say it's W. So gamma of water and the volume submerged. So the volume that is submerged, or the volume in the water, equals the buoyant force here is gamma of the liquid. Let's say that is gamma L. So say gamma L. And then the submerged volume here, so volume submerged, say L, BL. There. Now for the gamma of water, we have 9.81. And then the volume here is area times the height. There's no given area in the problem, so we will just put here A. So A, area, and then the height. The height being h minus 0.06. So h minus 0.06 equals gamma L. What's the gamma L here? Using the specific gravity of 1.2. So that is 1.20, 9.81. Then the volume, that would be area times the height. The height being h minus 0.08. H minus 0.08. So we can cancel out the area here. Cancel out the area. Cancel out the gamma of water. So what's left? H minus 0.06 equals 1.20 h minus That is 1.2 times 0.08. That is negative 0.096. Therefore, H now is equal to H is equal to 0.18 meter. So that's the answer for number 4. Let's go to the example number 5. A buoy in the form of a uniform 8-meter pole, 0.2 meter in diameter, has a mass of 200 kilograms and is secured at its lower end to the bottom of freshwater lake with a 5 meter cable. If water is 10 meters deep, determine the length of pole above the water surface. So this is the 8-meter pole. It's asking for the length of pole above the water surface. So it's asking for this one here. So that means this is X. Say X. So if this is X, this protruding this pole projecting upward, therefore this is 8 minus X. Right? Then it's asking for the vertical tension in the anchor cable. So the tension of this anchor cable here. Okay, for letter A, we're being asked for the value of X here. So how do we get that? We will use the principle of buoyancy. That would be the so we need to find the weight. What's the weight of the pole? So for letter A, we have the weight of the pole. Weight is it has a given mass of 200 kilogram. So we can find the weight because weight is equal to mass times gravity, and that is equal to, so that is 200 kilograms multiplied with 9.81 meter per second squared. So that is equal to 1962 kilogram meter per second squared. So that is 1962 Newton, or that is 1.962 kilonewton. Okay. And weight is always found at the center of gravity of the material. So here, so the center for this pole is at 4 meter length, and the weight is always projecting downward. Okay. So this is W, projecting downward, and this is 4 meters. Okay, so this is 4 meters. Okay, and how about the buoyancy? So buoyancy, the BF, is located at the center of the, okay, here, let's find the center of the submerged part of the pole. So that would mean buoyancy is around here, and it's projecting upward. So this is buoyant force, and the distance of this is, that would be 8 minus X divided by 2. So that's the distance of the buoyant force. So oops. is 8 minus x divided by 2. Okay? So if we are going to find the value for BF, or if we compute for BF, it would be buoyant force is equal to gamma of the liquid times the volume. So that is 9.81 for the liquid water, and then the volume is pi over 4. The diameter of the pole is 0.2 meter squared, and the height, so the area times the height, so the height here is 8 minus x. 8 minus x, so that is equal to 0.308 8 minus x. Then to find the values for buoyant force and the weight, let's have a summation of forces. Wait. So summation of forces, or summation of moment at here at point A. So summation of moment here. Summation of moment at A is equal to 0, positive counterclockwise. Therefore, we will find here the value for BF positive. But in order to rotate that, so we will be needing a perpendicular force perpendicular to the moment arm. So remember, this is our moment arm. So when we say moment arm, so the rotation is, so this is the pole. So if we rotate that, so the movement will be like this. So the rotation. So we need the moment arm. The force perpendicular to the moment arm. So if this is the pole, we need the buoyant force to be perpendicular to it, and the weight also perpendicular to the moment arm. So something like that. So we need the W here and the buoyant force here. So let's represent that component of forces with color green. So this is the for the weight, for the buoyant force, and this is for the weight. So this is weight normal, and then this is buoyant force normal, and then the angle formed here is the same angle formed with this pole. So this pole here, so this angle here is the same angle with this one, same angle, the same angle with this, and the same angle with this one. Okay, so those are the angle theta. So angle theta, this is angle theta. Therefore, we have here the force triangle W. So this is the WN. This is our force triangle. Here you go. So this is our force triangle here. It's so W. This is W. This is WN. This is perpendicular here, and then this is the angle. So the W is the hypotenuse. How about for the buoyant force? For the buoyant force, so this is the buoyant force. This is the component. And then, let's close the triangle. So this is buoyant force upward. And then this is the buoyant force component, so N. And buoyant force is the hypotenuse. And the angle here is theta. Okay. Therefore, we're looking for the Wn. So Wn here is equal to W cosine theta. Whereas for buoyant force is equal buoyant force N, or the component, that is equal to buoyant force cosine theta. So now we found the values for the BFN and Wn. So let's solve summation of moment at A. That is equal to buoyant force N sub N multiplied with the distance from the A. That would be perpendicular distance from A, 8 minus x over 2. So minus Wn, and its distance from the A here is 4 equals 0. So buoyant force N is BF N cosine theta, or BF, sorry, it's BF cosine theta, 8 minus x over 2 minus Wn is W cosine theta times 4 equals 0, or that is, okay, so equal to, so we can cancel out cosine theta. Then what's left here is BF. We have here the BF value, and then for the W, there goes our W. So BF is 0.308. 0.308, 8 minus x equals 8. Not yet. So we just input here BF times this one, the area, and the distance. So 8 minus x over 2 equals W here is 1.962 times 4. So x now is equal to 0.308 raised to, it would be 8 minus alpha x squared 2. Alpha equals 1.962 times 4. Subsolve. 0. Of course, it's not 15. X is not equal to 15 because the length of the pole is 8 meters. Therefore, the answer here is 0.861. So 0.861. Not, so 15 meters. This is greater than 8 meters. And this is wrong. Okay? This is not the answer. Rather, the answer here is this one. So that is the answer. So the next question here is B. Length, vertical tension in the anchor cable. So the anchor cable here is this. So letter B. We're going to cut the cable. So we cut that. So this is the pole. This is the cable. So if we cut the cable, we find here the tension. So the tension T. So you know that it's tension because the force is moving away from the point. Okay, so that is tension. This is our buoyant force. Our buoyant force here. And then we have the weight. This is W. So from here, you can have summation of forces vertical is equal to 0. W plus T is equal to buoyant force. W is 1.962 plus tension equals 0.308 times times 8 minus 0.86. So tension now is equal to 0.24 kilonewton. So that's for number 5. Okay, last problem, we have number 6. A cylindrical buoy, 600 mm in diameter and 1.8 meter high, weighs 205 kilograms. It is moored in salt water to a 12-meter length of a chain weighing 12 kilograms per meter of its length. At high tide, the height of buoy protruding above the water surface is 0.84 meter. What could be the length of protrusion of the buoy if the tide dropped 2.1 meter? Density of steel given here is 7,790 kilograms per cubic meter. Use density of water equal to 1,000 kilogram per cubic meter. Okay. So our buoy here is having two situations. The first one is at high tide, and the second one is when the tide dropped. Okay, when the tide dropped 2.1 meter. So it looks like this. This is the initial scenario, and this is the next scenario when the tide, okay, when the tide dropped 2.1 meter. So the difference of the two water level here, or the sea water level, is 2.1 meters. 2.1 meters. So same buoy. Here. So the height of the buoy, which is 1.8 meter high, is the same on both scenario. Okay. So let's put here the height. Meter. So this is 1.8 meter as well. Same. And then it says here that it is moored to a 12-meter length of chain. The chain is 12 meters in length. But of course you don't know if it's the total length of chain, the 12-meter length, is being used. So you're not sure if the chain is like this being used, or it could be like this. We don't know yet. The rest of the 12 meters is resting. That means it does not contribute to the weight that is pulling the buoy down, right? So that means at high tide, so at this high tide here, so this is the total length that is causing a weight on the buoy. Okay? Now, of course, at low tide, that length becomes smaller. So, cylindrical buoy, 600 in diameter, 600 mm. So, this is 600 mm, or that will be 0.6 meter diameter. At high tide, the height of buoy protruding above water surface is 0.84. So this is 0.84 here. So if this is 0.84, therefore this one here is 1.8 minus 0.84, 0.96. So this is 0.96 meter. So 0.96. What's being asked here is what could be the length of protrusion of the buoy if the tide dropped 2.1 meter. So if the tide dropped 2.1 meter, it's asking for the value of y here. So the value of y here. So it's asking for this, the value for y. So this y here is, so how do we get that? Of course, let's have this is L for the buoyant force. Let's say that is L. So that is then this is the height of the water or the sea water. And then when the tide dropped, this height of the water becomes let's assign it as h prime. Let's name that as h prime. Then since it went lower, therefore this becomes L prime. This is L prime, so let's name this as h prime minus L prime. H minus L becomes this. Okay? Therefore, you can find the value of y. Y now is equal to 1.8 minus h prime minus L prime. So this is our equation. So this is our equation 1. Now let's solve for situation A. At A, or the first situation, so let's name this as situation A, and this is situation B. High tide at A. So what can we see here? What are the forces that is present? So these are the weight. So this is the weight, same weight. Same weight. Weight 1. Same weight 1. And then the weight of the chain. So let's name that as W2. So weight of the chain. Of course, this is different now for the second scenario because there's a different L here. Length of chain. Then we have the buoyant force for the buoy. So buoyant force 1, and then we have buoyant force 2 for the chain, and then we have buoyant force 1 prime for the second scenario, and then buoyant force 2 prime for the chain in the second scenario. So these are the things that's happening. So in A, so same liquid, we are using here salt water. So the salt water, the given density for salt water specific gravity for salt water is 1.03. So at A, we have W1 plus W2 equals buoyant force 1 plus buoyant force 2. So the value for W1 is equal to, we have the given weight here for the buoy. There you go, 205 kilogram. So 205. So this is mass times gravity. So 205 kilograms times 9.81 meter per second squared for the gravity, gravitational acceleration. So that is 2.011 kilonewton. For W2, for the chain here, it says here, the chain weighs 12 kilogram per meter of its length. 12 kilogram per meter of its length. So that will be the 12 kilogram per meter of its length multiplied times length times the acceleration of gravity, 9.81 meter per second squared. So that is equal to 0.1177 L. Next, buoyant force 1 is gamma of the liquid, the salt water, times the volume submerged. So the salt water is 1.03 times 9.81 for its gamma L. And then for the volume, we have the pi over 4. The diameter is given as 0.6 meter diameter. So 0.6 squared. And then the submerged length, that is 0.96. So buoyant force 1 is equal to, or it is equal to 2.43 kilonewton. 2.743, sorry. 2.743 kilonewton. Next, buoyant force 2 is again gamma L volume, 1.03 times 9.81. The volume being the we need the volume of the chain. So we need the volume of the chain here. For the volume of the chain, because the density here, if you observe, the density of steel is given, so 7,790. So we can solve for the volume of the steel. Given the formula for density is equal to mass over volume. Let's use different color for that. So density is equal to mass over the volume. Therefore, volume is equal to the mass of 12 kilogram per meter. Right? Because it says here the mass is 12 kilogram per meter of its length. So that's the mass. And then the density is 7,790 kilogram per cubic meter. So the volume now is equal to 0.00154 cubic meter per meter. So we need per meter here, per meter length. So the volume now for BF2 is 0.00154 and then per meter length multiplied with length. So that is in every liter, in every meter of the chain, you have 0.00154. So that is equal to 0.0156 L, or the length. So we have now W1 as 2.011 plus W2 0.1177 L equals that would be BF1 is 2.743, and then BF2 is 0.0156 L. So what is now the value for L? So that is equal to 2.743 minus 2.011, so 0.1177 minus 0.0156, 156, 7.169. So that is 7.169 meter. It's not yet done because what we're looking for is the value for y. So it's not yet done. So now we have now the value of L. We can have the value of H. So for H is equal to 0.96 plus L, and that is equal to 0.96 plus 7.169. So H is now equal to 8.129 meters. So that's the value of H. So having had the value of H, can we get now the value of H prime? Okay, for H prime, look at this. This is H prime. So H prime is equal to H minus 2.1 in order to get the value for H prime. So repeat that. So for the value of H, that will be equal to the H minus 2.1 equals H prime. Okay. So H is equal, H prime is equal to H minus 2.1. So that is 8.129 minus 2.1. Therefore, H prime is now equal to 6.029 meters. So we now have the value for H prime. So look at the equation 1. We now have the value for H prime. Now, next we are going to look for the value for L prime. And we can get the value for L prime at situation B. So at situation B, we have here summation of forces vertical. So we have W1 plus W2. So W1 plus W2 prime minus BF1 prime minus BF2 prime. Okay. So that will be W1 plus W2 prime, that is equal to BF1 prime plus BF2 prime. So W1 is, of course, it's already the same, and we solved that. Same with situation A. So the weight of the buoy did not change, whereas the W2 prime for the length, for the weight of the chain changed because the length became smaller when the tide went low. So W2 prime is equal to 12 kilogram. So that is for the mass. So in every linear meter, right? In every L prime. And then we have the acceleration of gravity, 9.81 meter per second squared. So that is equal to 0.1177 L prime. For the buoyant force 1 prime, that is the submerged in the salt water, the liquid, then the volume of the liquid, submerged in the liquid. So BF1 here is the one submerged. So that is H prime minus L prime. Same area. Okay. So BF, that is 1.03, 9.81. Then the volume, pi over 4, diameter 0.6 squared, and then the height, which is H prime minus L prime. H prime being 6.029. So 6.029 minus L prime. So BF1 prime is 2.86, 6.029 minus L prime. So that is for buoyant force 1 prime. Then let's go to buoyant force 2 prime. That is again gamma L volume. So 1.03, 9.81. The volume, so we solved the volume a while ago. That is 0.00154. You recall? Here. And that is L prime. Instead of L, we are using L prime here. So BF2 prime is equal to, so that is equal to 0.0156 L prime. Then we now have W1 2.011 plus W2 prime 0.1177 L prime equals BF1 prime is 2.86, 6.029 minus L prime plus 0.0156 L prime for the BF2 prime. Now, what's the value for L prime? 2.011 plus 0.1177 alpha x, alpha equal to 2.86 times 6.029 minus alpha x minus, or that is plus 0.0156 alpha x. So 5.142 or 5.14 for the L. So 5.14 meter. Therefore, from our equation 1, so our equation 1 here, so y now is equal to 1.8 minus our h prime being 6.029 minus L prime of 5.14. So y now is equal to 0.911 meter. Okay, so that's the value for y. Okay, so that's number 6. Okay, so that ends our video.